What if everything you think you know about the universe is just the tip of an unimaginable iceberg? Picture this: the fabric of reality might not be what it seems. Black holes could be gateways to other realms. Dark matter might whisper secrets of dimensions beyond our grasp, and time itself, the steady, unshakable rhythm of our lives, could be nothing more than a cosmic illusion. This isn't science fiction. This is the cutting edge of cosmology, where the boldest minds are tearing up the rulebook and rewriting our understanding of existence itself. For centuries, we've relied on the laws of physics as our guiding light, trusting them to explain everything from falling apples to the orbits of planets. But what if those laws are just fragments of a far grander, far stranger truth? Theories like string theory suggest that the universe isn't made of particles at all, but of tiny, vibrating strings, threads in a cosmic symphony we're only beginning to hear. Quantum gravity hints that space and time might emerge from something deeper, like a hologram projected from the edge of reality, and the holographic principle. It turns our entire notion of the universe inside out, suggesting that everything we see might just be a shadow of a deeper, hidden reality. Why does this matter? Because these ideas aren't just abstract puzzles for physicists, they're keys to unlocking the greatest mysteries of existence. They challenge us to rethink what's possible, to question the very nature of reality itself. And in doing so, they invite us on a journey far more thrilling than any fiction. So buckle up. Over the next few minutes, we're diving into the wildest frontiers of science, where the answers might just rewrite everything, including what it means to be part of this universe. Ready to have your mind stretched? Let's begin. Imagine a world where falling apples and orbiting planets followed rules so perfect they seemed written in stone. That was the universe. Isaac Newton gave us a clockwork cosmos where gravity was a predictable force tugging objects together across empty space. For over 200 years, his laws held sway, explaining everything from tides to trajectories with elegant precision. But then came Albert Einstein, who peered deeper and realized something astonishing. Gravity wasn't a force at all. Instead, it was the very fabric of reality bending beneath the weight of matter. Picture spacetime as a stretchy trampoline, with stars and planets creating dimples that guide everything around them. This was general relativity, a theory so radical it reshaped our understanding of the universe overnight. Yet even Einstein's masterpiece had its limits. While relativity painted gravity as smooth and geometric, the quantum world was a frenzied dance of particles popping in and out of existence, governed by probability, not certainty. At the tiniest scales, the orderly cosmos fell into chaos. The clash was unavoidable. Relativity ruled the vast cosmos, while quantum mechanics dictated the subatomic realm. But the universe doesn't come with separate rulebooks. It's one interconnected whole. This glaring contradiction became the driving force behind modern cosmology, pushing scientists to seek a deeper theory, one that could unite these two giants of physics. The stakes couldn't be higher. Without reconciling these frameworks, we hit walls trying to explain black holes, the Big Bang, or even the nature of time itself. It's like having two keys to the same lock. Neither works alone. And that's where today's pioneers step in, armed with wild ideas like string theory and loop quantum gravity, each attempting to bridge the gap. But to appreciate how far we've come, we first had to pass through the crucible of Newton and Einstein, whose insights, flawed yet foundational, lit the path toward the mysteries we're still unraveling today. The quantum world is a place where certainty crumbles into probability, where particles flicker in and out of existence like fireflies in the dark. Here, electrons don't just orbit atoms, they exist in ghostly superpositions, spinning in all directions at once until measured. It's a realm governed by chance, where Heisenberg's uncertainty principle whispers that we can never precisely know both a particle's position and momentum at the same time. Yet, zoom out to the cosmic scale, and Einstein's general relativity paints a radically different picture. Here, spacetime is a smooth, geometric fabric, warped by massive objects in perfectly predictable ways. Planets orbit stars not through quantum randomness, but along elegant curves dictated by the very shape of the universe. The trouble begins when these two titanic theories collide. Picture a black hole where a star's collapse packs so much mass into such a tiny space that both quantum effects and gravitational extremes come into play. Relativity says the star's matter crushes into an infinitely dense point, a singularity, but quantum mechanics revolts, insisting nature abhors infinities. Similarly, at the Big Bang, when the entire universe was smaller than an atom, relativity's equations explode into nonsense while quantum rules strain to explain how space itself could emerge from nothing. It's as if the universe speaks two mutually unintelligible languages, one for the very small, one for the very large, and physicists are desperate to find the Rosetta Stone that translates between them. That's where string theory enters the stage. What if the fundamental building blocks of reality aren't particles at all, but unimaginably tiny strings, vibrating at different frequencies like the strings of a cosmic violin? In this framework, every particle, every force, even gravity itself, is just a different note in the universe's symphony. String theory tantalizingly suggests a way to weave quantum mechanics and relativity into a single mathematical tapestry. But there's a catch. These strings would exist in 10 or 11 dimensions, far beyond the 4 we experience. It's a breathtaking idea, but without experimental proof, it remains a beautiful hypothesis. Meanwhile, loop quantum gravity takes a starkly different approach. Instead of adding hidden dimensions, it reimagines spacetime itself as a network of woven loops, a fabric stitched together from discrete, indivisible threads. In this view, even space and time are quantized, emerging from interactions at the tiniest scales. It's like seeing the universe not as a smooth canvas, but as a pointillist painting up close. It's all dots, but step back, and the illusion of continuity appears. So which path leads to the truth? The answer might lie in the most extreme laboratories nature provides, black holes and the Big Bang. If we can decode what happens where gravity and quantum effects intertwine violently, we might finally glimpse the deeper reality stitching our universe together. Until then, the quest continues, not just for equations that work, but for a story so compelling it makes sense of everything from the spin of an electron to the whirl of galaxies. Because in the end, the universe doesn't owe us simplicity. It's our job to listen closely and decode its deepest rhythms. What if all the particles we've ever discovered, electrons, quarks, even the elusive Higgs boson, are just different notes in a grand cosmic melody? That's the radical promise of string theory, where the universe isn't built from point-like dots but from unimaginably tiny, vibrating strings. Imagine plucking a guitar string, tighten it, and the pitch rises. In this theory, every particle is just a string vibrating at a unique frequency. An electron isn't a speck. It's a string humming one tune, while a photon is the same string dancing to a different rhythm. Even gravity, the force that bends galaxies, emerges from this symphony, offering hope of uniting quantum mechanics and relativity at last. But there's a twist. For the math to work, these strings can't just wiggle in the 3 dimensions we know. They need room to move up to 11 dimensions, in fact. Think of it like a spider's web. To us, it's flat, but to a tiny ant crawling along its threads, it's a labyrinth of hidden pathways. string theory suggests extra dimensions are coiled into spaces smaller than an atom, curled so tightly we'd never notice them. Yet their existence could explain why gravity is oddly weak compared to other forces it might be leaking into these unseen folds of reality. The elegance of this idea is undeniable. A single framework explaining everything from the glow of stars to the glue holding atoms together. It's the kind of unified vision physicists have dreamed of for centuries. But beauty alone isn't proof. So far, no experiment has detected these strings or their extra dimensions. Critics argue it's less science and more sophisticated math, a theory so flexible it can't be disproven. After all, if the strings are too small to see and the dimensions too tiny to probe, how do we test it? Yet the allure persists. String theory's equations hint at staggering possibilities, like parallel universes or membranes, branes, for short, floating in higher dimensional space, each hosting its own cosmos. Some models even suggest the Big Bang wasn't a singular explosion but a collision between these branes, a cosmic car crash birthing our universe. It's speculative, yes, but that's the frontier, a place where the rules aren't just being broken, they're being rewritten. And whether string theory ultimately proves true or not, its boldness pushes us to ask deeper questions, to stretch our minds beyond the familiar dimensions of thought. Because sometimes the most revolutionary ideas aren't just answers, they're invitations to explore the impossible. What if the world around us, the trees, the stars, even your own hands, is nothing more than an elaborate cosmic projection? The holographic principle dares to suggest exactly that, turning our perception of reality inside out. This radical idea was born from an unlikely place, the study of black holes. When physicists calculated how much information a black hole could hold, they stumbled upon something astonishing. The maximum amount of data wasn't determined by the volume inside the black hole, but by the surface area of its event horizon. It's as if every bit of information about what's inside, every particle, every force, is somehow painted onto its outer boundary, like a cosmic mural encoding an entire universe in 2 dimensions. This revelation sparked a wild question. Could the same be true for our universe? Imagine a hologram where a flat, 2-dimensional surface creates the illusion of depth when light shines through it. The holographic principle proposes that our 3-dimensional reality might work the same way, a grand illusion projected from information stored on some distant, 2-dimensional surface at the edge of space. Every event, every object, even the passage of time itself, could be nothing more than shadows cast by data flickering on this unseen cosmic screen. The implications are staggering. If true, it would mean the universe operates like a colossal computer, with the boundary holding the source code and our 3D experience being the output. This challenges everything we thought we knew about space, matter, and even free will. After all, if we're just projections, does motion happen because objects move, or because the underlying data changes? But how could this possibly work? Some theories suggest that spacetime itself is pixelated at the tiniest scales, like a digital image where each pixel carries a fundamental unit of information. Just as a high-resolution image can fool the eye into seeing smooth curves, these spacetime pixels might weave together to create the seamless fabric of reality we perceive. Experiments are already underway to test this, using ultra-sensitive detectors to hunt for telltale fuzziness in the fabric of space that would betray its holographic nature. Critics argue it's a stretch without direct evidence. The principle remains a captivating what if. Yet its appeal lies in its audacity. It doesn't just tweak our understanding of physics, it upends it, suggesting that the universe is far stranger, far more interconnected than we ever imagined. Whether the holographic principle holds or not, it forces us to confront a humbling truth. Reality might not be what it seems, and in that uncertainty lies the thrill of discovery, the chance that the next breakthrough could reveal a universe even wilder than our boldest dreams. We've mapped galaxies, traced the birth of stars, even glimpsed the echo of the Big Bang, and yet everything we've ever seen, touched, or measured amounts to less than 5% of the universe. The rest, a cosmic blind spot dominated by two invisible enigmas, dark matter and dark energy. Think of them as the universe's hidden scaffolding and its mysterious engine. Dark matter is the unseen glue holding galaxies together, its gravitational pull keeping stars from flying apart like a spinning merry-go-round with no one holding on. Without it, our Milky Way would unravel, its spiral arms flinging into the void. But here's the catch, we've never directly detected it. It doesn't emit light, reflect it, or interact with ordinary matter in any way except through gravity. It's like trying to study a ghost by watching how it bends the air around it. Then there's dark energy, an even more perplexing force. In the late 1990s, astronomers made a shocking discovery. The universe isn't just expanding, it's accelerating, as if some invisible hand is pressing harder on the cosmic gas pedal. Dark energy is the name we give to whatever's causing this, but its nature is a complete mystery. Is it a property of space itself, a kind of anti-gravity woven into the fabric of reality? Or is it evidence of undiscovered physics, a sign that Einstein's equations need a radical update? The strangest part, these two phantoms might be connected. Some theories suggest dark matter could be made of particles that only interact through hidden dimensions, those same extra realms string theory proposes. Others speculate dark energy is the energy of empty space, fluctuating as parallel universes bubble in and out of existence in a vast multiverse. And then there's the boldest idea of all, that dark matter and dark energy aren't separate phenomena, but different faces of a single, deeper force we've yet to understand. The stakes couldn't be higher. If we crack this puzzle, we might finally answer why the universe looks the way it does, why galaxies cluster in vast cosmic webs, why the expansion rate defies expectation, even why life had the time and space to emerge. Experiments are hunting for dark matter particles deep underground, in particle colliders, and even in the quiet vacuum of space. Meanwhile, telescopes scan the skies for subtle distortions in starlight, mapping the invisible tug of dark matter's gravity. But perhaps the most mind-bending possibility is this. What if dark matter and dark energy aren't just filling the universe, but shaping its very structure? What if they're clues that our cosmos is just one thread in a far grander tapestry, woven from rules we're only beginning to guess, until we know one thing's certain: the universe is far stranger, far richer than we ever imagined, and the greatest discoveries lie not in the stars we see, but in the shadows they cast. While string theory dances with extra dimensions, loop quantum gravity takes a radically different approach. It suggests space itself is stitched together from tiny, indivisible threads. Picture the universe not as a smooth canvas, but as an intricate tapestry woven from microscopic loops, each one a fundamental knot in the fabric of reality. These loops don't exist within space. They are space, intersecting and linking to create the very geometry we experience. It's like zooming in on a piece of fabric until you see the individual threads, except here, the threads are the building blocks of spacetime itself. This bold idea solves one of physics' thorniest problems, the singularity at the heart of black holes and the Big Bang. In Einstein's equations, gravity becomes infinite at these points, tearing the fabric of reality. But loop quantum gravity says no, there's a smallest possible stitch in spacetime's weave, a limit to how tightly it can crumple. When matter collapses under gravity, it can't shrink to a dimensionless point. Instead, it reaches a maximum density and bounces back like a spring compressed to its limit. Imagine the Big Bang not as an explosion from nothing, but as the rebound of a previous universe that had collapsed. It's a cosmic reset, a universe recycling itself without infinities or singularities. The implications ripple outward. Time, in this framework, isn't a smooth river but a series of quantum jumps, like frames in a film too fast to perceive. Even causality, the idea that cause must precede effect, could emerge from these discrete steps rather than being fundamental. And black holes, they might not be eternal prisons. If spacetime is granular, information swallowed by a black hole could eventually escape, woven back into the cosmic tapestry as the whole evaporates. Yet loop quantum gravity faces its own challenges. Unlike string theory, it doesn't naturally incorporate other forces like electromagnetism. Critics argue it's a theory of gravity alone, leaving unification incomplete. And while its math avoids infinities, testing its predictions is fiendishly hard. The loops are unimaginably tiny, trillions of times smaller than an atom, making direct observation impossible with current technology. But here's what makes it extraordinary. It reimagines reality from the ground up, treating spacetime not as a stage where particles move, but as a dynamic, evolving network. It's a vision that feels almost medieval in its craftsmanship, a universe hand-stitched from loops where geometry is born from connection. Whether it's the final answer or just a stepping stone, loop quantum gravity reminds us that sometimes, to solve the deepest mysteries, we must rethink not just the rules, but the very fabric of the game. What if every choice you've ever made, every path taken or not taken, exists somewhere in an infinite cosmic tapestry? The multiverse hypothesis dares to suggest exactly that, proposing our universe is just one thread in a vast, shimmering web of realities. This isn't science fiction. It's a serious scientific idea born from the edges of quantum mechanics, string theory, and cosmic inflation. Picture a frothing ocean of spacetime, where bubbles of universes constantly form, each with its own unique physics. Some might have stars and planets like ours, while others could be cold, empty voids where gravity is too weak to clump matter together, or so strong that black holes dominate every corner. The roots of this idea stretch back to quantum mechanics, where particles exist in multiple states until observed. Take Schrödinger's famous cat, simultaneously alive and dead in its box. The many worlds interpretation takes this further, suggesting both outcomes happen, just in separate, branching universes. Every quantum decision, no matter how small, spawns new realities. Mr. Bus, somewhere out there, a version of you caught it, became an artist instead of a scientist. That timeline exists too. It's a dizzying thought, infinite versions of you, living infinite variations of your life. But quantum branching isn't the only path to a multiverse. Cosmic inflation, the theory that our universe expanded exponentially in its first moments, hints at something grander. If space stretched faster than light, pockets of it could have pinched off into isolated, bubble universes, each with different physical constants. Imagine blowing soap bubbles. Some are tiny, others enormous. Some pop instantly, while others drift for ages. In this cosmic foam, our universe might be one stable bubble among countless others, some collapsing immediately, others flourishing under alien laws. String theory adds another layer, suggesting higher dimensional brains could collide, birthing universes like ours in cosmic fireworks. These brains might float in an 11-dimensional bulk, never touching except in rare, cataclysmic events that spark new Big Bangs. It's a vision of creation not as a one-time event, but as an endless cycle of collisions and rebirths. Critics argue the multiverse is untestable, more philosophy than science. If we can't observe or interact with other universes, how do we prove they exist? Yet supporters counter that the math leads us there naturally, like realizing Earth isn't the center of the solar system. And if true, the multiverse could solve the fine-tuning puzzle, why our universe's constants seem perfectly calibrated for life. The answer: in an infinite ensemble of universes, a few must get the numbers right by sheer chance. We're not special, we're just lucky. Whether the multiverse is real or not, its power lies in the questions it forces us to ask. What does reality mean if most of it lies forever beyond our reach? Are the laws of physics truly universal or just local bylaws in our cosmic neighborhood? And if infinite versions of us exist, does that make our choices more meaningful or utterly insignificant? The multiverse doesn't just expand space, it expands imagination, challenging us to rethink not just where we are, but what we might be. Black holes have long been cosmic paradoxes, regions where the known laws of physics break down into screaming contradictions. Take the firewall paradox, a puzzle so unsettling it forces us to question whether Einstein's serene vision of spacetime can survive at the quantum edge. Here's the problem: quantum mechanics insists information can never vanish. Every particle, every interaction leaves an indelible mark on the universe, like footprints in cosmic sand. But black holes, by their very nature, seem to erase those footprints completely. Anything crossing the event horizon, whether a star, a book, or an unlucky astronaut, is lost forever, its information scrambled beyond recovery. That should be impossible. Enter the firewall hypothesis. If information can't be destroyed, perhaps it doesn't actually enter the black hole at all. Instead, it might pile up just outside the event horizon, forming a searing wall of energy, a firewall hotter than the core of a star. Anything touching it would be vaporized instantly, preserving the information while preventing it from ever reaching the black hole's interior. It's a brutal solution, but one that upholds quantum law. Yet this creates another crisis. Einstein's general relativity paints the event horizon as an unremarkable boundary, a point of no return, yes, but not a place of violence. If you fell in, you'd notice nothing special as you crossed. Space would stretch you gently, like taffy pulled toward the singularity. But a firewall shatters this elegant picture, turning the horizon into a cosmic kill zone. Both theories can't be right. Either quantum mechanics is wrong about information, or relativity is wrong about spacetime. The stakes are cosmic. If firewalls exist, they'd rewrite our understanding of black holes, revealing them not as smooth geometric objects, but as fringes of chaos where space itself fractures. Some theorists argue the paradox hints at a deeper truth, that spacetime isn't fundamental but emergent, like waves on an ocean. In this view, the smooth fabric Einstein described might dissolve at the tiniest scales, replaced by something far stranger. Others propose black holes are holograms with information encoded on their surfaces like a cosmic DVD, playing out the illusion of a three-dimensional interior. Experiments are impossible. No probe could survive a firewall to report back, but math offers clues. Recent work suggests the paradox might dissolve if we consider quantum entanglement, the spooky link between particles across vast distances. Perhaps the information isn't lost or burned, it's entangled in a way we're only beginning to untangle. Whatever the answer, the firewall paradox isn't just about black holes. It's a battle for the soul of physics, a clash between our two most successful theories, each refusing to yield. And in that tension lies a thrilling possibility, the key to unlocking quantum gravity, and with it, the universe's deepest secrets. Time flows like a river, always forward, never backward. We remember the past but not the future. Eggs scramble but never unscramble, and coffee cools but never spontaneously reheats. This one-way street of existence is so ingrained in our lives that we rarely stop to ask, why does time have a direction at all? The answer lies in a deceptively simple concept: entropy. According to the second law of thermodynamics, entropy, a measure of disorder, always increases in a closed system. It's the reason heat spreads, structures decay, and the universe marches relentlessly toward a state of maximum chaos. But here's the twist: the laws of physics themselves don't care about time's arrow. Flip the equations and they work just as well backward. So why does time stubbornly move forward in our experience? Some physicists argue time's flow isn't fundamental but emergent, a side effect of something deeper. One provocative idea ties it to quantum entanglement, the bizarre phenomenon where particles become linked across space. Every time particles interact, their entanglement grows, weaving a web of connections that only gets more complex. This increasing entanglement might create the illusion of time's flow, like a cosmic clock ticking forward as the universe becomes more intertwined. Another theory points to the expansion of the universe itself. As space stretches, it pulls matter apart, creating new possibilities for disorder, and with it, an inexorable rise in entropy. The Big Bang might have set the initial low entropy state, like winding up a clock, letting it unwind ever since. But if time is emergent, what does that mean for free will? If the future is just the unfolding of quantum probabilities or entropic inevitability, are our choices real or illusions woven into the fabric of causality? Some interpretations suggest that even in a block universe where past, present, and future exist simultaneously, our perception of time grants us agency within the slice we call now. Others propose that free will operates within the constraints of physics, like a river carving its path through bedrock. The water's flow is determined by gravity, but its exact route emerges from countless tiny interactions. The implications ripple further. If time isn't fundamental, could it vanish in extreme conditions like inside a black hole or at the quantum scale? Some models of quantum gravity suggest spacetime itself dissolves into a froth of probabilities, where before and after lose meaning. Even causality, the bedrock of science, might be provisional, a shorthand for deeper, timeless laws. Yet for all its mystery, time's arrow shapes everything: the birth and death of stars, the evolution of life, even the firing of neurons in our brains. Whether it's an illusion or an emergent property, one thing's certain: the universe is telling a story, and the plot only moves in one direction. What if the universe isn't just governed by laws of physics, but by lines of code? The simulation hypothesis takes the digital age's most familiar concept and flips it into a cosmic question. Could everything we see, touch, and experience be part of an unfathomably advanced simulation? Think of it like this: a century ago, video games were clunky pixels bouncing on screens. Today, we craft entire virtual worlds with realistic physics, weather systems, even artificial intelligence. If technology keeps advancing, future civilizations might create simulations indistinguishable from reality. So why couldn't we be inside someone else's version? This isn't just sci-fi speculation. Philosopher Nick Bostrom formalized the idea with a chilling trilemma. Either civilizations never reach the tech level to run such simulations, they choose not to, or most unsettlingly, we're almost certainly living in one. The logic is statistical. If advanced civilizations exist, they might run countless ancestor simulations to study their past. The number of simulated minds would dwarf biological ones, making odds overwhelming that we're among the digital, not the original. But how could we test such a wild idea? Some scientists propose looking for glitches, in reality tiny errors a programmer might overlook, like a video game where distant objects simplify to save processing power. Maybe our universe cuts corners at extreme scales. Physicists have hunted for pixelation in spacetime or anomalies in high-energy particle collisions, but so far, reality seems suspiciously flawless. Others suggest quantum indeterminacy. The randomness of particle behavior could be the simulation's way of reducing computational load, like a computer skipping decimal places to save memory. Critics dismiss it as pseudoscience, an untestable metaphor, not physics. After all, if the simulators control every variable, how could we ever prove we're not part of their design? Yet supporters counter that the hypothesis reshapes how we view foundational mysteries. Dark energy may be just a placeholder value in the code, quantum superposition. The universe rendering outcomes only when observed, like a game loading graphics as you explore. Even consciousness could be an algorithmic illusion, a convincing subroutine tricking us into feeling real. The simulation argument does something remarkable. It turns cosmology into a detective story, where every unexplained phenomenon becomes a potential clue. Whether it's true or not, it forces us to confront the unnerving possibility that reality might have layers we've barely begun to scrape. And if we are in a simulation, the biggest question isn't about the programmers. It's about what happens when their subjects start figuring out the truth. Einstein called it spooky action at a distance, a phrase dripping with skepticism about quantum entanglement's bizarre implications. Yet today, this phenomenon isn't just real. It's the backbone of quantum technologies and a profound challenge to our classical intuition. Picture two electrons born from the same quantum event, their spins intrinsically linked. Separate them by miles or even light years, and measuring one instantly determines the state of the other, as if they're whispering secrets across the void faster than light could travel between them. This isn't theoretical. Experiments have confirmed it repeatedly, with particles communicating their states across lab benches, through fiber optic cables, even between satellites in orbit. The implications shatter a cornerstone of classical physics: locality, the idea that objects can only be influenced by their immediate surroundings. Entanglement suggests a hidden layer of reality where particles remain mysteriously connected, indifferent to the space between them. It's as if the universe keeps a secret ledger, updating entries simultaneously no matter how far apart the pages are. Einstein hated this. He insisted there must be hidden variables, unknown properties determining particles' behavior in advance. But in the 1960s, physicist John Bell devised a test to settle the debate. The results were unequivocal: no hidden variables. The spookiness was real. Now, the real mystery isn't just how entanglement works, but what it means for the fabric of reality. Some theorists propose it's a clue to quantum gravity, the missing link between relativity and quantum mechanics. If entangled particles know each other's states instantly, perhaps spacetime itself emerges from a vast network of quantum connections like threads weaving the illusion of a continuous fabric. Others go further, suggesting entanglement might underpin the holographic principle, with the universe's information encoded in boundary-like relationships between particles. Then there's the tantalizing and controversial idea of quantum communication. Could we harness entanglement to send messages faster than light? The quantum no-cloning theorem dashes most hopes. You can't copy or control an entangled state without breaking the link. Yet breakthroughs in quantum teleportation, transferring quantum information across distances, hint at revolutionary technologies, from unhackable networks to quantum internet prototypes already being tested. At its heart, entanglement forces us to confront a radical truth. the universe might be far more interconnected than we ever imagined. It's not just particles that are linked, it's the very notion of separation that might be the illusion. And if that's the case, the next great leap in physics won't just change our theories. It could redefine what reality even means. The Big Bang paints a vivid picture of our universe's explosive birth, a fiery expansion from an unimaginably dense, hot singularity nearly 14 billion years ago. But here's the puzzle that keeps cosmologists awake. If the Big Bang was the beginning, what set it in motion? Classical physics hits a wall here, collapsing into infinities and paradoxes. Yet cutting-edge theories are now daring to peek behind the cosmic curtain, proposing scenarios far stranger than anything we've imagined. One compelling idea is the cyclic universe model, where the Big Bang wasn't a singular event but one in an endless series. Picture a cosmic accordion, expanding and contracting over trillions of years. Each bang is followed by a crunch, as gravity eventually reverses the universe's expansion, pulling everything back into a singularity only for another Big Bang to ignite. In this view, time has no true beginning or end. It's an infinite loop of creation and destruction. Some versions even suggest that collisions between higher dimensional branes, floating membranes of reality, could trigger each new cycle, like sheets of paper slapping together in a cosmic wind. But there's another, even wilder possibility, that the Big Bang emerged from a seething quantum foam. At the tiniest scales, spacetime isn't smooth and continuous but a turbulent froth of bubbles flickering in and out of existence. In this quantum chaos, fluctuations could occasionally grow large enough to spawn entire universes, ours being just one accidental bubble in an endless, foaming sea. Theories like loop quantum gravity take this further, suggesting the singularity might not have been a point of infinite density but a bounce, where a previous universe collapsed and rebounded like a rubber band snapping back. Then there's the holographic twist. If our universe is a projection from a two-dimensional boundary, the Big Bang might represent the moment this cosmic hologram booted up. Information encoded on the edge of space could have unfolded into the three-dimensional reality we know, like a movie reel spinning to life. The challenge. Testing these ideas, without a time machine, we can't witness the Big Bang directly, but subtle clues might linger. Gravitational waves from the universe's earliest moments could carry imprints of pre-Big Bang physics, like echoes of a collision between branes. The cosmic microwave background, that faint glow from the infant universe, might hide patterns betraying a cyclic past or quantum origins. What's thrilling isn't just the diversity of theories, it's how they force us to rethink existence itself. If time is cyclical, does cause and effect still hold meaning? If we're a quantum bubble, are there other universes with entirely different laws? The Big Bang might not be the ultimate beginning, but a doorway, one leading to questions as vast as the cosmos they aim to explain. Einstein's theory of general relativity has been the gold standard for gravity for over a century, a masterpiece that explains everything from the bending of starlight to the dance of black holes. But what if it's not the final word? A growing number of physicists are daring to ask whether gravity itself might need an update, especially when it comes to the vast scales of galaxies and galaxy clusters. The problem is dark matter, that invisible, mysterious substance we've never directly detected, yet seems to hold the universe together. But what if dark matter doesn't exist at all? What if gravity just works differently than we thought? Enter modified Newtonian dynamics. This radical idea suggests that instead of invoking unseen matter, we might just need to tweak the laws of gravity, especially where they seem to fail. Newton's and Einstein's equations work flawlessly in our solar system, predicting planetary orbits with pinpoint accuracy. But when we look at galaxies, something's off. Stars on the outer edges of spiral galaxies rotate faster than they should, as if gripped by an invisible hand. Dark matter was the conventional fix, but Mund offers an alternative. Maybe gravity doesn't weaken as sharply with distance as we've assumed. At extremely low accelerations like those far from a galaxy's center, gravity could strengthen slightly, just enough to explain those runaway stars without any dark matter required. The evidence is intriguing. Some galaxies, particularly ultra-diffuse ones, match Mund predictions better than dark matter models. Others show gravitational effects that align neatly with modified gravity, no hidden particles needed. Even more compelling, Mund predicted certain galactic behaviors before they were observed, something dark matter theories often struggle with, but it's not a perfect solution. While Mund excels at galaxy-scale puzzles, it stumbles when applied to galaxy clusters or the cosmic web large-scale structures where dark matter still seems to hold sway. Critics argue Mund is a patch, not a true theory, lacking the mathematical elegance of general relativity. It also doesn't explain other dark matter evidence, like gravitational lensing patterns or the cosmic microwave background's fluctuations. Yet supporters counter that science progresses by questioning even our most cherished ideas. After all, Newton's gravity was revolutionary until Einstein showed it was incomplete. Could we be on the brink of another paradigm shift? The debate isn't just academic. If Mund is right, it would upend decades of cosmology, forcing us to rewrite the rules of the universe. If it's wrong, it's still a bold reminder that even Einstein's genius isn't sacred, that the best science thrives on skepticism, daring to ask, what if we've been missing something fundamental all along? Either way, the pursuit is a testament to the most thrilling part of physics, the chance that the next breakthrough might come from questioning the very foundations we take for granted. Black holes are cosmic shredders, swallowing everything that crosses their event horizon: stars, gas, even light itself. But here's the twist: they might not be the ultimate trash compactors we once thought. Thanks to Stephen Hawking's groundbreaking work, we now know black holes aren't entirely black. They emit a faint glow of particles, now called Hawking radiation, slowly leaking energy and shrinking over unimaginable eons until they vanish entirely. This raises a cosmic whodunit. If the black hole evaporates, what happens to all the information it consumed? Quantum mechanics insists information can't be destroyed. Every particle, every interaction leaves an indelible mark on the universe, like a fingerprint. Yet general relativity suggests black holes erase everything they swallow, crushing matter into a featureless singularity. This clash is the information paradox, a crisis at the heart of physics that forces us to question whether our most fundamental laws are incomplete. If information really vanishes, quantum mechanics is wrong. If it doesn't, Einstein's gravity might need rewriting. One audacious solution comes from the holographic principle, which suggests black holes don't destroy information, they encode it. Like a cosmic hard drive, the event horizon might store data about everything that fell in, imprinting it onto Hawking radiation as the black hole evaporates. Imagine burning a book. The ashes seem random, but in theory, if you could track every molecule's trajectory, you could reconstruct the original text. Similarly, Hawking radiation might carry scrambled but intact information, waiting to be decoded. Then there's the wormhole twist. Some theories propose black holes don't destroy information but funnel it through hidden tunnels in spacetime into other universes. It's as if the black hole is a cosmic printer, with the original data spat out in a parallel reality. This idea, while speculative, finds surprising support in the math of quantum entanglement. where particles separated by vast distances remain mysteriously linked. Could black holes exploit similar connections, preserving information by spreading it across the multiverse? But the boldest idea of all is that information never enters the black hole to begin with. The firewall hypothesis suggests a searing wall of energy at the event horizon vaporizes anything approaching, converting it into pure information that radiates away. It's a brutal solution, turning black holes from gentle cosmic traps into blazing infernos, but one that neatly sidesteps the paradox by ensuring data never crosses the point of no return. The stakes couldn't be higher. If information escapes, black holes might be cosmic archivists, not executioners. If it's lost, the foundations of quantum theory crumble. And if it's shuffled into other dimensions, well, that's a story even physics isn't ready to end. Supersymmetry is the elegant idea that every particle in the universe has a hidden twin, a mirror image partner waiting to be discovered. Picture a cosmic dance where electrons, quarks, and photons are all paired with heavier, unseen siblings, each balancing the equations of quantum physics like perfect counterweights. This theory, affectionately nicknamed SUSY by physicists, isn't just mathematical poetry. It could solve some of the biggest puzzles in modern science, like the identity of dark matter or why gravity is so weak compared to other forces. The math is undeniably beautiful. Supersymmetry smooths out the jagged edges of quantum field theory, eliminating infinities that plague calculations and offering a path to unify nature's forces under one framework. It also provides a tantalizing candidate for dark matter, the lightest supersymmetric particle, or LSP. This hypothetical particle wouldn't interact with light or ordinary matter, making it invisible, yet its gravity could explain why galaxies hold together. It's a compelling package, one theory that tidies up quantum mechanics, bridges relativity, and accounts for the universe's missing mass, but there's a catch. After decades of searching, not a single supersymmetric particle has shown up in particle colliders like the Large Hadron Collider. The simplest versions of SUSY predicted these partners should appear at energies we've already probed. Their absence has left some physicists skeptical, while others argue we've simply been looking in the wrong place. Maybe supersymmetric particles are far heavier than expected, or they decay too quickly to detect. The stakes are high. If SUSY is real, its discovery would be as transformative as Einstein's relativity, rewriting textbooks overnight. If it's wrong, physicists must confront an uncomfortable truth. The universe's elegance might not match our aesthetic preferences. Some are already exploring alternatives, like extra dimensions or composite particles, while die-hard SUSY supporters await higher energy colliders that could finally reveal these elusive twins. What makes supersymmetry so captivating isn't just its potential, it's the way it mirrors science's greatest leaps. Like Copernicus moving Earth from the universe's center, or Darwin linking humans to ancient ancestors, SUSY challenges us to see reality differently. Whether it's confirmed or discarded, the quest itself reveals something profound. Our universe's secrets are never just lying in plain sight. They're hidden in the math, waiting for the right moment and the right minds to bring them into the light. Consider the cosmic lottery we've somehow won. The strength of gravity, the charge of an electron, even the exact energy levels in atomic nuclei. If any of these values shifted by a hair, stars wouldn't ignite, chemistry would crumble, and life as we know it would be impossible. This eerie precision is the heart of the fine-tuning problem, a puzzle that's haunted physicists for decades. Why does the universe seem custom-built for our existence? The anthropic principle offers a deceptively simple answer. We're here to ask the question precisely because the numbers lined up just right. If they hadn't, no one would be around to notice. But this isn't just circular logic, it's a lens that reshapes how we think about reality. Take the cosmological constant, the energy density of empty space. If it were slightly stronger, the universe would have ripped apart before galaxies formed. Slightly weaker, and gravity would have crushed everything back into a singularity. The odds of it landing in the narrow life-permitting range are astronomically small, like rolling a die and getting the same number 1,000,000,000,000 times in a row. The anthropic principle suggests there's no deeper reason. We just happen to live in the rare universe where the dice fell kindly. Multiverse theories take this idea and run with it. Imagine a cosmic kaleidoscope where every twist creates a new universe with different physical constants. Most might be barren voids where gravity is too weak for stars or electromagnetism too strong for stable atoms. But in a few, by sheer chance, the numbers align perfectly. We're not special, we're just the winners of a cosmic jackpot with near infinite tickets. It's a humbling thought. Our entire universe might be one accidental success in a sea of failures. Critics argue this is a cop-out, a way to dodge the search for deeper laws. Why invoke countless unseen universes when we could instead seek a theory that explains why our constants have the values they do? Some theorists propose alternatives, like the idea of a self-tuning universe, where physical laws evolve dynamically to permit complexity. Others suggest the constants aren't arbitrary at all but mathematically inevitable, locked into place by undiscovered symmetries. Yet the anthropic principle lingers because it forces us to confront the limits of human-centric thinking. We instinctively search for purpose, for design, but what if the universe isn't for us? What if we're just the fleeting byproduct of impersonal probabilities? Whether it's a sobering truth or a challenge to dig deeper, one thing's certain: the fine-tuning puzzle isn't just about physics. It's about our place in a cosmos that may not care we're here at all. Every second, trillions of nearly invisible particles streak through your body like cosmic ghosts, neutrinos, the universe's most elusive messengers. These subatomic wraiths are so indifferent to matter that a neutrino could pass through a light year of solid lead without a single collision. Yet their very existence defies our understanding of reality. According to the Standard Model, the rulebook of particle physics, neutrinos should be massless like photons. But experiments reveal they do have mass, just impossibly tiny. A single neutrino weighs less than 1/1,000,000th of an electron, a discrepancy that cracks open the door to physics beyond our current theories. The plot thickens with neutrino oscillations, perhaps their strangest trick. As these particles travel through space, they morph between three flavors: electron, muon, and tau neutrinos. It's as if a strawberry suddenly turned into a banana, then an orange without warning. This bizarre behavior only makes sense if neutrinos have mass, confirming the Standard Model's blind spot. But here's the real kicker. Oscillations imply that neutrinos might hold clues to one of cosmology's biggest puzzles: why the universe is made of matter at all. In the earliest moments after the Big Bang, matter and antimatter should have annihilated each other perfectly, leaving behind nothing but empty space. Yet here we are, neutrinos, with their subtle asymmetry in behavior between particles and antiparticles, might be the reason matter won that ancient cosmic duel. Some theories suggest heavy, right-handed neutrinos yet to be detected could have tipped the scales, seeding the universe with just enough leftover matter to form galaxies, stars, and eventually us. Hunting these phantoms requires ingenuity. Detectors like Japan's Super Kamiok and a colossal tank of ultra-pure water buried deep underground wait for the rare flash of light when a neutrino finally bumps into an atom. IceCube, an observatory drilled into Antarctic ice, tracks even rarer high-energy neutrinos from cataclysms like colliding black holes. Each capture peels back another layer of the mystery, but the biggest questions remain. Are there sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity? Could neutrino masses hint at extra dimensions or a grand unified theory? What makes neutrinos so thrilling isn't just their defiance of expectations, it's their potential to rewrite physics. They're whispers from the universe's hidden rulebook, carrying secrets we're only beginning to decode. And with every new discovery, these ghostly particles remind us, the most profound truths often lie just beyond what we can see. What if gravity, the force that pins us to Earth and steers planets in their orbits, isn't a fundamental part of nature at all? Imagine it's more like temperature, not a thing in itself, but a collective effect of something deeper. That's the startling premise of emergent gravity, a theory that turns our cosmic rulebook inside out. Instead of spacetime bending to create gravity, this idea suggests gravity is spacetime, a side effect of more basic ingredients, like the way waves emerge from the chaos of ocean molecules. The roots of this thinking trace back to black holes. When physicists calculated their entropy, a measure of disorder, they found it wasn't tied to their volume but to their surface area. It's as if all the information inside a black hole gets painted onto its boundary, a concept echoing the holographic principle. Dutch physicist Erik Verlin took this further, proposing that gravity isn't a force but an entropic one. Picture a crowd of people jostling in a room. Their movements create statistical tendencies like drifting toward exits. In Verlin's view, gravity is the universe's version of this, a tendency that arises from the natural drive toward disorder, not some intrinsic pull between masses. Quantum entanglement adds another layer. If particles are linked across space, their connections might weave the very fabric of spacetime itself. Gravity, then, could be the way this network responds when masses distort its threads, like weights stretching a spider's web. This perspective unifies gravity with quantum mechanics in an elegant twist. Both emerge from information exchange between particles. No more need for dark matter. Either galaxies' odd rotations might just be how this cosmic web behaves at vast scales. But can we test such an abstract idea? Surprisingly, yes. If gravity emerges from entropy, its strength might vary slightly where entropy gradients shift, like near galaxy edges. Some observations of distant stars already hint at anomalies matching these predictions, though the data isn't conclusive. Other experiments probe whether spacetime has a quantum structure, which would support the idea of gravity as a secondary effect. Critics argue emergent gravity lacks the precision of general relativity, failing to explain phenomena like gravitational waves in detail, yet its allure lies in its simplicity. By demoting gravity from a fundamental force to a cosmic illusion, it offers a path past the stalemate between quantum theory and relativity. Whether it's right or not, it forces us to ask, are we mistaking the universe's shadow for its substance? And if gravity is just a symptom of deeper laws, what other forces might be waiting to be explained away? In the first moments after the Big Bang, the universe didn't just expand, it exploded outward faster than the speed of light, doubling in size over and over again in fractions of a second. This mind-bending concept, called cosmic inflation, solves one of cosmology's biggest puzzles: why the universe looks so smooth and uniform in every direction we observe. Without inflation, distant regions of space would never have had time to even out their temperatures, yet the cosmic microwave background, the afterglow of the Big Bang, shows near-perfect uniformity across billions of light years. It's as if someone took a lumpy batter and whipped it into a perfectly smooth consistency in an instant. But what could possibly power such an extreme growth spurt? The leading suspect is a hypothetical energy field called the inflaton, a kind of cosmic spring that briefly sent spacetime stretching at an unimaginable rate. Picture a ball rolling down a hill, gathering speed, except in this case, the hill is an energy landscape, and the ball is the early universe trapped in a high-energy state. As the inflattened field decayed, its energy flooded the universe, heating it into the fiery plasma we recognize as the Big Bang's aftermath. Quantum fluctuations in this field would have been stretched to cosmic scales, seeding the tiny density variations that later grew into galaxies and galaxy clusters. The implications are staggering. Without those random quantum jitters, the universe might have remained a featureless void, devoid of stars, planets, or life. Inflation doesn't just explain the universe's smoothness, it explains its texture, the delicate wrinkles that made structure possible. Yet the theory isn't without its mysteries. What exactly was the inflaton? Some models suggest it could be related to the Higgs field, which gives particles mass. Others propose it was a unique, short-lived phenomenon, a burst of energy unlike anything in today's universe. Even stranger, inflation might not have been a one-time event. Eternal inflation theory suggests that some pockets of space never stopped expanding exponentially, spawning endless bubble universes with different physical laws. Our cosmos could be just one frothy region in an infinite multiverse where other bubbles experience entirely different realities. If true, it would mean the Big Bang wasn't the absolute beginning, just the start of our local story. Testing these ideas pushes the limits of observation. Astronomers hunt for primordial gravitational waves, ripples in spacetime from inflation's violent expansion, imprinted on the cosmic microwave background. Others study the large-scale distribution of galaxies, looking for patterns only inflation could produce. The evidence so far is tantalizing but incomplete, like finding footprints but not yet seeing the creature that made them. What makes inflation so compelling isn't just its explanatory power, it's the way it reshapes our origin story. The universe didn't unfold in a steady, predictable march. It began with a wild, exponential leap, a moment of unimaginable transformation that set the stage for everything to come. And if we can decode its secrets, we might finally understand not just how our universe began, but whether it's truly alone. The universe is unimaginably vast, billions of galaxies, each with billions of stars, many hosting planets in the so-called Goldilocks zone where life could thrive. Given those odds, the cosmos should be teeming with civilizations. So why does the sky stay silent? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The eerie absence of extraterrestrial contact forces us to confront unsettling possibilities about life, intelligence, and the fate of civilizations. One answer is simple: maybe we're alone. Life could be vanishingly rare, requiring such a precise cocktail of conditions that Earth is a cosmic fluke. Even if simple life emerges, the leap to complex organisms might demand miracles like the Cambrian explosion, a sudden burst of biodiversity 500 million years ago that might never repeat elsewhere. And intelligence, it took 4 billion years of evolution on Earth. If predators, ice ages, or asteroid strikes had played out slightly differently, humans might never have appeared. The universe could be littered with microbes or barren altogether, but let's say life is common. Why wouldn't advanced civilizations announce themselves? One chilling possibility is the Great Filter, a catastrophic hurdle that wipes out societies before they can spread across the stars. It could be nuclear war, runaway AI, ecological collapse, or some danger we haven't yet imagined. If the filter lies ahead of us, humanity's future might be bleak. If it's behind us, like the unlikely rise of DNA, we might already be survivors of a cosmic bottleneck. Then there's the zoo hypothesis. Aliens know we're here but choose not to interfere, observing us like animals in a wildlife preserve. Or perhaps spacefaring cultures transcend physical travel, uploading their minds into virtual realms or manipulating dimensions we can't perceive. Imagine ants unaware of the internet. Could we be missing signals in forms of communication beyond light and radio waves? The paradox also reshapes how we search. SETI scans for radio signals, but what if advanced civilizations use neutrino beams or quantum entanglement? Others suggest looking for Dyson spheres, megastructures harvesting a star's energy, or atmospheric pollution on distant worlds. Even our assumptions about aliens might be flawed. They could be post-biological, their ships more like self-replicating nanobots than Star Trek starships. The Fermi Paradox isn't just about aliens, it's a mirror. Every solution reflects our hopes, fears, and biases. Are we special or just early? Are we doomed or simply uninteresting? Until we find answers, the silence of the cosmos remains the most profound question of all. The human brain is often called the most complex object in the known universe, a 3-pound tangle of neurons firing in patterns that somehow give rise to thoughts, memories, and self-awareness. But how does mere matter produce the vivid light show of consciousness? Some scientists argue the answer might lie not in classical biology, but in the bizarre realm of quantum physics. At first glance, the idea seems outrageous. Quantum effects typically vanish in warm, wet environments like living tissue. Yet a handful of researchers propose that delicate quantum processes could persist inside microtubules, tiny protein structures within brain cells, acting as the missing link between physics and experience. This radical theory, orchestrated by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests consciousness arises from quantum vibrations within these microtubules. When these vibrations collapse a process tied to quantum gravity, they generate moments of awareness like pixels flickering into the movie of our minds. It's as if the brain isn't just a computer, but a quantum orchestra with each note representing a fleeting thought or sensation. If true, it would mean our inner world isn't just shaped by chemistry, but by the fundamental fabric of reality itself. Critics dismiss the idea as wishful thinking, pointing out that quantum coherence where particles stay mysteriously linked would struggle to survive the brain's noisy environment. Even in cutting-edge quantum computers, maintaining coherence requires near-absolute zero temperatures and painstaking isolation. How could something so fragile persist in the swirling chaos of our skulls? Yet supporters counter that nature might have evolved workarounds, like biological shielding or rapid quantum computations that outpaced decoherence. After all, photosynthesis, a process essential to life, relies on quantum effects in green plants. Could the brain harbor similar tricks? The implications ripple far beyond neuroscience. If consciousness taps into quantum physics, it might not be confined to the brain at all. Some interpretations suggest the mind could interact with spacetime's underlying structure, blurring the line between observer and observed. This echoes ancient philosophies and modern physics alike, where reality seems to respond to measurement. Even more provocatively, if quantum processes bind consciousness to the cosmos, could awareness be a universal property woven into existence itself? Whether the quantum consciousness theory holds water or not, it forces us to confront profound questions. Are we just biological machines, or does our experience hint at deeper connections to the universe? The answer might lie not in philosophy or physics alone, but in the uncharted territory where they collide. Until then, the mystery of consciousness remains one of science's last great frontiers, a puzzle as intimate as our next thought and as vast as the cosmos. Empty space isn't really empty. Even in the deepest void, where no stars shine and no particles drift, the universe is alive with potential, a seething quantum foam where particles flicker in and out of existence like bubbles in a cosmic champagne glass. This bizarre behavior, predicted by quantum field theory, means nothing is anything but virtual particles pop into being, borrowing energy from the vacuum before vanishing again, all within the blink of an eye. It's as if the universe refuses to sit still, constantly buzzing with activity even in its quietest corners. This raises a profound question. If even emptiness teems with energy, could the entire universe have sprung from nothing? Some theories suggest our cosmos might be a quantum fluctuation on an unimaginable scale, a random burp in the fabric of reality that, against all odds, didn't immediately fizzle out. Imagine a balloon inflating from a single, fleeting bubble in an infinite ocean of nothingness. The odds are infinitesimal, but given eternity, even the impossible might become inevitable. Yet this idea clashes with our intuition. How can something come from nothing without violating the conservation of energy? The answer might lie in gravity's unique role. While energy is always conserved locally, the gravitational field of the entire universe could balance the books, with negative gravitational energy perfectly cancelling out the positive energy of matter and light. In this view, the total energy of the cosmos might be zero, meaning no fundamental law was broken when it burst into being. But why is there a universe at all? Philosophers like Leibniz pondered this for centuries, and modern physics offers startling possibilities. Some theories propose a multiverse where countless universes bubble up endlessly, each with different physical laws. Most might collapse instantly or remain barren, but a rare few, like ours, strike the perfect balance for existence. Others suggest existence is inevitable, that the very concept of nothing is unstable, always collapsing into something due to quantum instability. The most radical idea comes from quantum gravity, where spacetime itself might emerge from a deeper, abstract network of relationships. In this framework, asking, why is there something rather than nothing? Could be like asking why a rainbow exists separate from sunlight and rain. The components only create the phenomenon when arranged just so, implying existence isn't a miracle, but a natural consequence of deeper principles we're still unraveling. Whether the answer lies in quantum chaos, multiverses, or undiscovered physics, one thing's certain: the mystery of existence pushes us to the very edge of science and philosophy. And in that tension between the measurable and the unimaginable, we find not just answers but better questions. Einstein's equations hold a tantalizing secret. Hidden within the math are tunnels weaving through the fabric of spacetime itself, wormholes, cosmic shortcuts that could connect distant corners of the universe in the blink of an eye. Picture folding a piece of paper so 2 points touch, then punching a hole through them. That's the essence of a wormhole, a bridge bending space so dramatically that traveling between galaxies might take minutes instead of millennia. Theoretically, these structures are perfectly valid solutions to general relativity, but there's a catch. Wormholes would snap shut instantly without something to prop them open, something called exotic matter, a hypothetical substance with negative energy that defies gravity's pull. Exotic matter isn't just rare, it's unlike anything we've ever seen. Normal matter, like planets or stars, creates gravity that pulls spacetime inward. Exotic matter would do the opposite, pushing spacetime outward like anti-gravity, counteracting the wormhole's natural collapse. The problem: we've never observed it. Quantum physics hints that negative energy might exist in microscopic amounts. Think of the fleeting quantum foam bubbling in a vacuum. But scaling that up to stabilize a wormhole would demand engineering far beyond our grasp. Yet if traversable wormholes could exist, the implications would rewrite the rules of reality. Need to visit a star system 1,000 light-years away. Step through a wormhole and you might arrive before lunch. Even wilder, wormholes could twist time as well as space. If one end were accelerated to near light speed or placed near a black hole, time would slow there relative to the other end, effectively creating a time machine. Walk in one side and you might emerge centuries in the past or future. But here's where things get thorny. Time travel introduces paradoxes like the infamous grandfather paradox, where going back to alter the past could erase your own existence. Physics might prevent such inconsistencies through mechanisms we don't yet understand, like quantum effects that reroute causality or self-correcting timelines. Alternatively, wormholes might only allow travel to moments after their creation, sidestepping paradoxes entirely. The biggest hurdle isn't just finding exotic matter, it's surviving the journey. Theoretical models suggest wormholes would be riddled with lethal radiation, gravitational tides strong enough to shred atoms, and instabilities that could collapse the tunnel mid-transit. Even if we overcame those dangers, there's no guarantee wormholes would be stable long enough to be useful, or that they wouldn't destabilize space-time itself on cosmic scales. For now, wormholes remain in the realm of theory, a dazzling what-if at the edge of known physics, but their allure isn't just about shortcuts through space or glimpses of the past. They're a test, a challenge to see how far our equations can take us before reality pushes back. Whether they're cosmic highways or mathematical mirages, wormholes remind us that the universe's strangest possibilities often lie just beyond the horizon of the impossible. The fate of the universe hangs in the balance between two opposing forces, expansion and gravity. For over a century, we've known the cosmos is stretching outward, galaxies fleeing from one another like dots on an inflating balloon. But will this expansion continue forever, or could gravity eventually reverse it, pulling everything back into a fiery collapse? The answer lies in a cosmic tug of war whose outcome depends on secrets we've only begun to uncover. Current observations point toward a cold, lonely finale known as heat death. As the universe expands, galaxies will drift further apart until their light can no longer reach us. Stars will exhaust their fuel, black holes will evaporate via Hawking radiation, and space itself will approach absolute zero, a state of maximum entropy where no energy remains to power motion, thought, or even the flicker of a single electron. Time in this scenario becomes meaningless. With no temperature differences to drive change, the universe settles into eternal stillness, like an ember fading to ash. Yet heat death isn't the only possibility. If dark energy, the mysterious force accelerating expansion, weakens over time, or if the universe contains enough matter, gravity might ultimately prevail. Picture a ball thrown upward. If it has enough speed, it escapes Earth's pull forever. But if not, it eventually falls back. In a Big Crunch scenario, the universe's expansion would slow, halt, and reverse, collapsing galaxies, stars, and atoms into an ever-shrinking inferno. Space would heat up as it contracts, culminating in a singularity mirroring the Big Bang, a cosmic reset that could spawn a new universe in an endless cycle. The wild card is dark energy. If it strengthens rather than weakens, it could tear space-time apart in a big rip, shredding galaxies, planets, and even atomic nuclei in a final cataclysm. Alternatively, quantum fluctuations in the vacuum could spawn a new bubble universe, birthing fresh cosmic landscapes beyond our own. What makes these questions more than theoretical is how they reshape our understanding of time. If the universe is doomed to heat death, time's arrow points irreversibly toward disorder. But in a cyclic cosmos, time might loop back on itself, with entropy resetting in each new cycle. The difference isn't just academic, it's about whether existence is a one-act play or an endless drama with infinite encores. For now, the evidence leans toward heat death. The universe's expansion is accelerating, not slowing, but with 95% of the cosmos still unexplained dark matter, dark energy, quantum gravity, our predictions rest on shaky ground. The ultimate fate of reality might hinge on physics we haven't yet discovered, hiding in the voids between galaxies or the quantum foam of spacetime. Until then, the universe keeps its final secret close, leaving us to wonder, will it end with a whisper, a crunch, or something stranger still? In the quantum realm, particles can exist in a surreal dance of possibilities, an electron spinning both clockwise and counterclockwise at once, a photon passing through two slits simultaneously. Yet when we look, this strange superposition vanishes, leaving behind a single, definite state. Why don't we see these quantum superpositions in our everyday world? The answer lies in a process called decoherence, the silent force that bridges the quantum and classical realms, turning the bizarre into the familiar. Imagine a drop of ink falling into a glass of water. At first, its path is clear, a single, coherent streak. But as the ink interacts with the water molecules, it spreads, dispersing until the entire glass is tinted uniformly. Decoherence works similarly. When a quantum system like an atom or photon interacts with its environment, whether through stray photons, air molecules, or even the faintest gravitational tug, its delicate superposition becomes entangled with countless external particles. This entanglement effectively leaks quantum weirdness into the environment, leaving the system in a state we recognize as classical, one outcome, not many. This isn't just a theoretical curiosity. Decoherence solves one of quantum mechanics' most vexing puzzles, the measurement problem. Early theorists like Schrödinger and von Neumann wrestled with the idea that observation collapses a quantum state, raising thorny questions about the role of consciousness. Decoherence sidesteps this by showing that collapse isn't mystical, it's inevitable. The moment a quantum system interacts with anything macroscopic, its superposition unravels. A cat in a box might be both alive and dead in theory, but in reality, the cat's own body heat, the air around it, even the box's atoms trigger decoherence instantly, locking in a single outcome long before a human lifts the lid. The implications stretch far beyond textbooks. Quantum computers rely on maintaining coherence, preventing decoherence long enough to perform calculations in multiple states at once. That's why they're kept at temperatures near absolute zero and shielded from even the faintest electromagnetic noise. A single stray photon can destroy the fragile quantum states powering their immense speed. On the flip side, decoherence explains why we don't see quantum effects in daily life. Your coffee cup doesn't tunnel through the table because its trillions of particles are constantly jostled by the environment, pinning it firmly in place. But here's the twist: decoherence doesn't eliminate quantum weirdness, it redistributes it. The information about all possible states isn't lost, it's woven into the environment like whispers drowned out by a crowd. Some physicists argue this hints at a deeper truth, that the classical world emerges from quantum foundations, not as a separate layer, but as a consequence of scale and interaction. The universe isn't split into quantum and classical, it's all quantum, just perceived differently depending on how closely we look. This realization reshapes our understanding of reality itself. What we call observation might just be the universe's way of making its endless possibilities tangible, one decoherent moment at a time. And in that shift from the probabilistic to the concrete lies not just the answer to a quantum riddle, but a glimpse into how the fabric of existence stitches itself together. In the early 20th century, mathematician Kurt Gödel dropped a bombshell on the foundations of logic, a revelation so profound it reshaped our understanding of truth itself. His incompleteness theorems proved that in any sufficiently complex mathematical system, there will always be statements that are true but impossible to prove within that system's own rules. It's as if you wrote a dictionary but couldn't define every word without using the words themselves, a paradox lurking at the heart of knowledge. Now, imagine applying this idea to physics. If even mathematics, the language of the universe, has built-in limits, could the same be true for our quest to decode reality? At first glance, physics seems different. Unlike abstract math, it's grounded in observation. We test theories against the real world, but dig deeper and the parallels emerge. Take quantum mechanics. We can predict particle behavior with astonishing precision, yet we still debate what it means. The math works flawlessly, but the underlying reality, whether particles exist in multiple states or collapse upon observation, remains philosophically murky. This isn't just ignorance, it might reflect a Gödel-like limit. Our theories describe nature's behavior, but they may never reveal its ultimate why. The implications ripple outward. If physics is incomplete, a theory of everything could remain forever out of reach. String theory, for all its elegance, offers countless possible solutions, a landscape of universes with different physical laws. Without experimental proof, we might never know which one corresponds to our reality. Even worse, some truths about the cosmos could be fundamentally unprovable from within it. Imagine trying to read a book while trapped inside its pages. You'd never see the full story. Yet this isn't despair, it's liberation. Gödel's work doesn't mean science is futile. It means curiosity is endless. Every answer spawns new questions, and the universe's deepest secrets might not be solvable puzzles, but invitations to wonder. After all, the stars shone long before we understood nuclear fusion, and their beauty wasn't diminished by our ignorance. Perhaps the greatest lesson isn't about limits, but humility, the recognition that some mysteries aren't meant to be broken, only embraced. Imagine a world where reality doesn't exist until you look at it, where particles have no definite properties until a conscious observer measures them. This isn't science fiction. It's the heart of the Copenhagen interpretation of quantum mechanics, one of the most provocative ideas in modern physics. At its core is the measurement problem. Why do quantum superpositions, those ghostly states where particles exist in multiple possibilities, collapse into a single outcome the moment we observe them? The Copenhagen answer is startling. Observation itself creates reality. In this view, the universe isn't a fixed, objective backdrop, but a fluid, participatory dance between the observer and the observed. But what does observation really mean here? It's not about human consciousness in the everyday sense. The Copenhagen interpretation defines it as any interaction that leaves a measurable mark, a photon hitting a detector, an electron scattering off another particle. Yet the ambiguity lingers. If a machine records data without a human ever seeing it, has the wave function still collapsed? This subtlety has fueled debates for decades, with some arguing that consciousness, whether human or otherwise, plays an irreducible role in shaping reality. Nobel laureate Eugene Wigner took this further, proposing thought experiments where a friend's observation inside a lab could keep a system in superposition until Wigner himself became aware of the result. It's as if reality remains unsettled until it enters someone's mind. Not everyone finds this satisfying. Alternative theories like Bohmian mechanics reject the need for observers altogether. Here, particles have definite positions at all times, guided by hidden pilot waves that steer their paths deterministically. It's a throwback to classical intuition, but with a quantum twist. The pilot wave encodes all the weirdness of superposition and entanglement just behind the scenes. No collapse, no observer dependence, just an invisible hand nudging particles along their way. Then there's the many worlds interpretation, which sidesteps the issue entirely by declaring that every quantum possibility plays out in a branching multiverse. In this sprawling cosmic tapestry, there's no collapse because every outcome happens somewhere. You measure an electron spin and the universe splits. One version of you sees up, another down. No special role for consciousness, just endless parallel realities. The debate cuts to the heart of what science is. Is the universe a collection of facts waiting to be discovered, or does it somehow depend on our interaction with it? The Copenhagen interpretation leans toward the latter, suggesting that the act of measurement isn't passive but creative. Critics call this borderline mysticism, arguing that physics should explain the world as it is, not as we perceive it. But supporters counter that quantum mechanics is the most accurate theory we have, and if it says observation matters, we shouldn't dismiss that lightly. Perhaps the truth lies in the gaps between these views. Maybe consciousness isn't the magician conjuring reality, but a lens focusing it, one perspective among countless others in a vast, interconnected whole. Or maybe we're asking the wrong question, entirely framing quantum weirdness in terms that make sense to our classical brains, like ants trying to comprehend the internet. Whatever the answer, the role of consciousness in physics remains one of the deepest, most contentious mysteries, a reminder that sometimes the hardest thing to measure isn't the universe, but our place within it. Imagine a clock that ticks forever without ever being wound, a structure that moves, changes, even oscillates, all without consuming energy or slowing down. This isn't a perpetual motion machine forbidden by the laws of physics. It's something far stranger, a time crystal, a bizarre new phase of matter that defies time's most basic assumptions. In 2012, Nobel laureate Frank Wilczek first theorized their existence, suggesting that just as ordinary crystals repeat their atomic patterns in space, time crystals could repeat their patterns in time, oscillating indefinitely without energy input. The idea was so radical that many physicists dismissed it as impossible. Yet just 5 years later, experiments with chains of ions and diamond defects proved time crystals were real, ushering in a revolution in how we think about matter, energy, and time itself. What makes time crystals so extraordinary is their ability to break time symmetry, a fundamental principle stating that the laws of physics work the same whether time runs forward or backward. A swinging pendulum, for example, obeys this symmetry. Play the footage in reverse and it looks just as natural, but time crystals don't play by these rules. Their atomic structures spontaneously lock into rhythms, flipping between states at fixed intervals, creating a form of perpetual motion that doesn't violate thermodynamics because it doesn't produce usable energy. Think of it like a dance where the performers move in perfect sync, returning to their starting positions over and over, not because they're driven by music, but because the dance itself is written into the fabric of their existence. The secret lies in quantum entanglement. Time crystals emerge when particles become so intricately linked that their collective behavior stabilizes into a repeating cycle, resistant to disturbances. In one experiment, researchers used lasers to nudge a chain of ytterbium atoms into this entangled state, like a row of dominoes that endlessly flipped themselves back up after falling. The atoms kept cycling between configurations long after the initial push, their rhythm unbroken by external noise. This robustness hints at staggering applications, particularly in quantum computing. Today's quantum bits or qubits are notoriously fragile, collapsing at the slightest disturbance. Time crystals could act as ultra-stable quantum memory, preserving information in their unyielding rhythms even in chaotic environments. But the implications run deeper than technology. Time crystals challenge our understanding of equilibrium, the state where systems settle into thermal balance. Ordinary matter, like a cup of coffee cooling to room temperature, eventually reaches equilibrium and stops changing. Time crystals, though, never do. They're a new class of non-equilibrium matter, proving that even in the most dormant conditions, the quantum world can harbor hidden dynamism. Some theorists speculate they might even model exotic cosmic phenomena, like the theoretical time loops near black holes or the cyclical universes imagined in certain cosmologies. Perhaps the most tantalizing question is whether time crystals could reshape our concept of time itself. If matter can encode rhythmic change into its fundamental structure, could time be more than a backdrop? Could it emerge from the collective behavior of quantum systems? We're only beginning to glimpse the answers, but one thing's certain: time crystals aren't just a new material. They're a doorway into a world where time, matter, and quantum magic intertwine in ways we're only starting to dream of. Black holes have long been cosmic enigmas, swallowing information and locking it away behind an impenetrable event horizon. But what if the universe has a clever escape route, a way for information to slip free without breaking any rules? Recent breakthroughs suggest black holes might not be the ultimate vaults we once thought. Instead, they could be cosmic magicians, performing quantum sleight of hand to preserve information in ways we're only beginning to understand. One audacious idea comes from quantum teleportation, the same phenomenon that lets particles vanish in one place and reappear in another instantaneously. If entangled particles near a black hole's edge can relay their states outward via this spooky connection, information might bypass the horizon entirely, hopping across the void like a message passed through a chain of quantum whispers. Even stranger is the holographic solution. Imagine the event horizon as a buzzing, pixelated screen, encoding every bit of information that falls into the black hole, not in its depths but on its surface. Like a cosmic QR code, this two-dimensional boundary could store data in Planck-sized units, then slowly radiate it back out as Hawking radiation evaporates the black hole. The math suggests this isn't just metaphor. Black holes might literally be holograms with their interiors projected from information painted on their edges. If true, it would mean the three-dimensional universe we perceive could itself be a grand illusion, a shadow cast by deeper, flat realities. The stakes go far beyond black holes. If information can escape or was never truly trapped, it could bridge the chasm between quantum mechanics and gravity. Quantum theory insists information is indestructible, while general relativity allows black holes to erase it. Reconciling these views might require rewriting our understanding of spacetime itself. Some theories propose spacetime isn't fundamental, but emerges from quantum entanglement, like a 3D tapestry woven from threads of information. Every particle interaction, every gravitational tug could be a stitch in that fabric. Experiments are already testing these ideas. Quantum computers simulate holographic principles, while telescopes hunt for anomalies in Hawking radiation that might betray hidden data. Even if the answers remain elusive, the quest itself is transforming physics. Black holes, once thought to be the universe's ultimate dead ends, might instead be the key to unlocking its deepest secrets, showing us that information doesn't just fill space and time. It might be what builds them. The Big Bang isn't the only story the universe could tell. Before it became cosmology's cornerstone, rival theories vied for dominance, and some still linger at the fringes, challenging us to reconsider even our most basic assumptions. Take the steady-state model, once a formidable competitor to the Big Bang. Proposed in the 1940s by Fred Hoyle and others, It painted a cosmos without beginning or end, eternally expanding while new matter continuously popped into existence to fill the gaps. Imagine a river flowing forever, its waters constantly renewing so the stream never thins. This elegant vision avoided the singularity problem entirely, sidestepping the need for a cosmic starting gun. But by the 1960s, the discovery of the cosmic microwave background, the afterglow of the Big Bang, seemed to deal steady state a fatal blow. Yet whispers of its legacy remain. Some theorists still ask, could pockets of the universe behave this way, with quantum fields mimicking steady-state conditions on local scales? Then there's plasma cosmology, a radical reimagining where electromagnetic forces, not gravity, sculpt the cosmos. In this view, swirling currents of ionized gas plasma could generate galaxy-spanning magnetic fields, shaping cosmic structures without invoking dark matter. Picture the universe as a vast electric circuit, with filaments of glowing plasma threading through space like neon signs in a cosmic city. Proponents point to laboratory experiments where plasma self-organizes into spiral structures eerily reminiscent of galaxies. Yet mainstream cosmology dismisses these ideas, citing overwhelming evidence for gravity's dominance. The clash isn't just about data, it's a philosophical battle over which forces deserve the spotlight in the cosmic drama. Even more speculative is the cyclic universe, where big bangs and big crunches repeat in an endless loop. Borrowing from Hindu cosmology's concept of kalpas, this model suggests our universe is just one page in an infinite cosmic book. Each cycle begins with a bang, expands, contracts, and rebounds into the next. Unlike steady state, cyclic models embrace singularities but argue their transitions, not in points. They eliminate the need for a definitive beginning, offering a universe that's always been and always will be. Yet the math is fiendishly complex and evidence remains elusive. Without proof of previous cycles, the theory dances on the edge of metaphysics. What unites these alternatives isn't their viability, but their audacity. They remind us that science thrives on dissent, that every paradigm, no matter how entrenched, was once a heresy. The Big Bang itself faced ridicule when first proposed, dismissed as pseudoscience cloaked in biblical imagery. Today's fringe ideas might be tomorrow's textbooks, or they might fade into obscurity, but their value lies in the questions they force us to ask. What if dark matter is a mirage, a sign we've misunderstood gravity? What if the Big Bang wasn't the beginning but a phase in a grander cycle? The universe owes us no answers, only mysteries, and sometimes the wildest theories light the path to the truth. Science has taken us from deciphering the motion of planets to peering into the quantum foam of spacetime, but will this journey of discovery ever reach an end? The unsettling truth is that some cosmic questions might forever lie beyond our grasp, not because we lack ingenuity, but because the universe itself may have built-in barriers to understanding. Consider the event horizon of a black hole. By definition, it's a boundary beyond which information can't escape. If the universe has similar cognitive horizons, regions where the answers are intrinsically shielded from observation, no amount of technological advancement would let us see past them. Take dark energy, the mysterious force accelerating the universe's expansion. Its effects are measurable, but its nature remains opaque. Some theories suggest it's woven into the vacuum of space itself, a fundamental property we can describe mathematically but never fully explain, like asking why the speed of light is what it is. Even worse, if the universe's expansion eventually isolates galaxies beyond our observable reach, future cosmologists might gaze into a night sky nearly empty of stars, their cosmic history erased by the very forces they're trying to study. The evidence they need could be forever unreachable, receding faster than light can chase it. Then there's the quantum realm, where the act of measurement alters the system being observed. At some point, probing reality too closely might distort it beyond recognition, like trying to study a snowflake by gripping it in a fist. The Planck scale, the smallest meaningful unit of space and time, hints at this limit. Below it, spacetime may lose all meaning, dissolving into a probabilistic froth where before and after have no significance. Could a theory ever describe such a realm in terms our brains evolved to comprehend? Or would it be like explaining color to someone born blind? Yet history offers a counterpoint. Every era's scientists believed they'd hit the limits of knowledge, only for revolutions to shatter those assumptions. When Lord Kelvin declared physics nearly complete in the late 1800s, he couldn't imagine relativity or quantum mechanics lurking just around the corner. Today's unanswered questions might simply await their own paradigm shifts, tools or frameworks we haven't yet invented. String theory and loop quantum gravity, for all their uncertainties, represent this stubborn human refusal to accept unknowable as a final answer. The deeper challenge might not be the universe's secrets, but our own minds. Evolution shaped us to navigate a middle world, to avoid predators, track seasons, and build tools. Concepts like higher dimensional geometry or timeless quantum states strain the very architecture of our cognition. Imagine teaching calculus to a goldfish. Some truths might require intelligences radically different from our own. Artificial superintelligence or post-biological civilizations could one day bridge this gap, but they'd still face the existential question: does reality allow a complete theory, or is knowledge an infinite fractal, revealing ever deeper layers the closer we look? Perhaps the most humbling thought is that ultimate answers might not exist at all. The universe could be a patchwork of emergent phenomena, with no why beneath its patterns, just mathematical contingencies stacking into complexity. In that case, the quest for understanding becomes not a march toward finality, but an endless, glorious exploration. And isn't that more thrilling? A cosmos that always keeps one last card up its sleeve, ensuring the story never truly ends. From string theory's vibrating dimensions to the holographic principle's illusion of depth, modern physics isn't just revising the rulebook, it's burning it down and rewriting it from scratch. These aren't incremental tweaks to old ideas, they're seismic shifts that force us to rethink the very fabric of existence. Take black holes, once thought to be cosmic dead ends. Now they're laboratories for quantum gravity, their event horizons buzzing with encoded information, their interiors possibly gateways to other universes. Or consider dark matter, that invisible scaffold holding galaxies together. It might not be matter at all, but a shadow cast by unseen dimensions or a flaw in our understanding of gravity itself. Everywhere we look, the universe defies expectation, revealing layers of complexity that make even the wildest science fiction seem tame by comparison. What makes this moment so electrifying isn't just the audacity of these theories, it's their stakes. If the holographic principle holds, our 3D reality could be a projection from a distant 2D surface, like a shadow puppet cast by the universe's underlying code. String theory's extra dimensions might explain why gravity is so weak, or why particles behave the way they do. And if emergent gravity is real, Einstein's spacetime could be an illusion, a collective effect of quantum entanglement weaving the cosmos together. These aren't abstract thought experiments, they're potential keys to unlocking everything from the nature of time to the origin of the universe. Yet for all their brilliance, these ideas are still hypotheses, waiting for the experiments that will confirm or shatter them. That's the thrilling paradox of modern physics. The more we learn, the more we realize how much we don't know. The Large Hadron Collider, gravitational wave detectors, and quantum simulations are pushing the boundaries of observation. But some answers might lie just beyond our reach, hidden in the Planck scale foam of spacetime or the distant edges of an accelerating cosmos. And that's okay. Uncertainty isn't failure, it's an invitation. Every unanswered question is a frontier, waiting for the next curious mind to explore it. So where does that leave us, in a universe that's stranger, richer, and more mysterious than we ever dared imagine? A universe where time might emerge from quantum entanglement, where black holes could be holograms, where the laws of physics might be local bylaws in an infinite multiverse. This isn't the end of discovery. It's the beginning of a new chapter, one where the biggest breakthroughs might come from questioning the assumptions we didn't even realize we had. Whether you're a physicist, a student, or just someone who gazes up at the stars and wonders, remember, the greatest discoveries start with a simple thought. What if, keep asking, the universe